از پروفسور دین دعوت به عمل میاد که تشریف بیارن و سخنرانی کلیدشون رو ارائه بفرمایند.
Well, thank you very much. First of all, I would like to thank the conference organizers for the very kind invitation and the wonderful chance to visit Iran. I would also like to thank and compliment the organizers, the directors of the conference board, and also the various committees. I know how much work it is to organize a conference like this, and it's very evident that the organizers have worked very hard and diligently. Well, this morning I'd like to discuss some recent work, in fact it's still ongoing, related to sea level acceleration. And first of all, I'll define acceleration, although I realize that most of you here are engineers and probably doesn't need definition. But acceleration is important because it relates to what sea level is going to do in the future and, of course, what it's done in the past. If we look at the pink line here, the upper line, it shows an acceleration greater than 0, and that means that it's going to, or has increased rate of rise with time. The middle line, where acceleration is 0, is just a straight line. And then negative acceleration is shown here as curving downward. And this is a very simple equation that we're going to be examining. It's a quadratic equation. And the A1 here would be the rate of sea level rise, and A2 would be the acceleration. So A2 again could either be positive or negative, and that's going to be the focus of my talk. And one of the main reasons for studying acceleration is that I think in the United States, and also I think worldwide, there has been a lot of work done, a lot of projections, and there remains a lot of uncertainty in trying to estimate what sea level will do into the future. And of course it's very important because if we plan for a large rise, that's going to be expensive. But if a large rise occurs and we don't plan for it, that could be equally expensive. In the United States, the initial work was done in 1984, and you can see that the range of estimates was between 0.51 meters by the year 2100 and 3.28. And the Intergovernmental Panel on Climate Change, there have been 4 of those. The next one is in 2013. And you can see that by and large the upper range has come down somewhat, and the lower range more or less as well. At the present time, the Corps of Engineers, one of our primary governmental agencies, is planning on between 0.17 meters and 1.5 meters. Now, 1.5 meters would be enormously expensive, so that's basically what we're considering. Just a little bit of background. Sea level has risen at an average rate of about 1.7 millimeters per year over the 20th century. The rate of rise is predicted to accelerate, and that's pretty much uniformly, I think, around the world. And that's based primarily on numerical models. And so we're going today to look at some 20th century tide gauge data. Tide gauge data, of course, are really one of the bases that we have to determine sea level. This, again, is some of the guidance that is used by the U.S. Army Corps of Engineers. And they have three different projections. One is straight line, no acceleration. One is by 2100, a rise of 0.5 meter. And then the upper one would be a range of 1.5 meters by 2100. And I'd like to point out, we're going to be talking about some numbers, some quantitative values. I'd like to point out that this upper curve is an acceleration of 0.2 millimeters per year squared. So if you could just kind of keep that in mind, that if you had something like 0.2 millimeters per year squared, then by 2100 you'd have a increase of 1.5 meters. Some of the reasons that we were interested in this, I've been working with a colleague, by the way, Dr. Jim Houston, is the recent satellite data starting in 1993 indicated that sea level was rising at that time at greater than 3 millimeters per year. Again, the rate we're accustomed to is about 1.7. And the question was, is that a trend? There was confusing information provided to policymakers, a lot of disagreement amongst investigators, and we've discussed that. Just to mention that there are other contributors besides ourselves that can contribute to sea level rise, is the sunspot activity. And fortunately, we have about 300 years of sunspot activity at Edinburgh, Scotland, and some of that's shown here. The first satellite altimetry went up in late 1992, and you can see that on the bottom scale here is shown millimeters per year, and you can see that around the world, on the world's oceans, the rate of sea level rise is not uniform. There's high degrees of variability over in the Western Pacific. Some areas are rising over this 15-year period at something like 10 times the average. Off the west coast of the United States, sea level has actually declined slightly over that 15-year period. So one of the points is we do need a very long record. So this is what I'll try to present to you today. Some of the analysis results from U.S. tide gauges, and then describe some analysis results from long-term worldwide gauges, and also I'll comment on the satellite altimetry results. Our results are completely data-based. We don't address the disintegration of the West Antarctic ice sheet, for example. And our data source is, there's a permanent service for mean sea level in Liverpool. Here's the website. And it's a wonderful site. They have all of the gauges that are reported to them, and some of these gauges are very long-term. Just as an example, the closest long-term gauge I could find relatively closely to Iran was Mumbai, India. And the site that I mentioned a moment ago in Liverpool includes both average monthly data and average yearly data. And on the lower panel, I've shown the 1.7 millimeters per year. Again, that's probably what's happened over the last century, as near as we can tell. And you can see that it's higher than at Mumbai. But of course, there are other motions or other effects. We have ground motion, either up or down. We have glacial isostatic adjustment due to the last ice age occurring, etc. The longest term gauge in the U.S. is San Francisco, California. It's 156 years long. And in the lower panel, you can see that the 1.7 millimeters per year is probably pretty good agreement with those data. Well, basically, we, again, there are two parts. We formed two data groups. We've tried to look at high-quality, long records. And one of these data groups had 80 years of tide gauges records. The other had more than up to 100 or more. Analyzed it two ways. We're looking for a small signal. We think the acceleration is going to be small, but important at any rate. So we averaged the tide gauge records. I'll show you an example of that. And then we analyzed for acceleration and trend. And in the other second method, we first analyzed each record and then averaged the accelerations and trends. We have not corrected our data for our results for vertical ground motion. And the reason we haven't is that acceleration should be insensitive to vertical ground motion if that vertical ground motion is stationary over the period of the record. So we haven't, although I'll show you some of the results. So the first part of our study, we used 18 gauges and with greater lengths than 80 years and less than 5% missing data. Again, we're trying to segregate or select data that only are of high quality. And here you can see the locations of the gauges. Have one in Alaska, Skagway, and one in Hawaii, and the rest on the continental U.S. So here are the monthly average of those 18 U.S. gauges with record lengths of greater than 80 years and less than 5% missing data in each record. And that's shown in the upper panel here. And you can see it's a noisy record. First of all, you see the annual spikes, and that's due to the heating and cooling of the oceanic waters where those tide gauges are located, usually in a port or on the shore. That's, first of all, that's a steric effect, the heating and cooling. You can also see this irregularity, and some of those are due to El Nino events. Some of them we can see what they're due to. But the important thing is that, one can at least visually see what the average record has done for over 80 years. The lower panel simply shows the dropouts in the data. And for example, if there were no data gaps at all, this number would be 18. But you can see we have something like up to 3 gauges dropping out at one time. Overall, the data availability the data losses were 1.1%. Again, any particular record had maximum 5%, but overall it was 1.1%. Well, we've analyzed those data both for trend, and that's the upper plot here, and acceleration, the lower plot. And going back 80 years, the start date was 1930. And so we've analyzed from 1930 to 1940. That would be the first data point. 1930 to 1940 plus a month. That would be the second point, and so on and so forth. And you can see that the data are quite noisy. They don't settle down until you get out to almost 2010. That would be 80 years. So this point is the trend for 80 years of analysis. This point is the acceleration for 80 years of analysis. The interesting feature of this is that the acceleration is by and large negative. There are a few times when it becomes positive. And I think that was a surprise because, at least in our country, all the agencies are planning on a positive acceleration. We're going to look at just the last part of that acceleration record because it was very close to zero. And you can see that this again would be 80 years of data, and that would be, we started in 1930, that'd be 60 years of data. So we're looking at the last 20 years of the acceleration, and it is all negative. And you can see it more or less, I'd say, settles down about minus 0.01. Remember, some of the guidance that has been issued was plus 0.2. So this would mean a very slow, very small slowing down of the data. I won't spend much time on this, but the second data group was for records over 100 years, and again, less than 5% missing data. And we had 10 such records in the U.S., and that is shown here. I think in your mind's eye, or at least in my mind's eye, maybe I'm a little bit biased, but I can see a negative acceleration there. Next slide, and we're going to look mainly at the accelerations, although we have the trends here as well. But you can see for the first data group, we have these 2 analysis methods. First data group, analysis method 1. is minus 0.013, and analysis method 2 is minus 0.0105. And then if we look at the gauges that have 100 years of record, there are only 10 of those, but you can see that those are likewise negative. Not so much negative, but they were likewise negative. So that's the part one of the study, and again, we found that if you look at the best quality U.S. gauges, the sea level is decelerating, slowing down at a very, very slow rate. Our part two study was patterned after a person who's quite eminent in the U.S. in terms of his work on sea level change. And in 1992, he studied 23 long-term worldwide gauges and found a negative acceleration of about what we found, minus 0.01 millimeters per year squared. And his data were for 80 years. So we've extended his analysis using the same gauges such that we now have 105 years. And we'll look at that. This is a table. What he did was he divided the world's ocean into sectors. And for example, in data group 1, there were 9 tide gauges in that area represented by data group 1. He didn't include each of them individually, but he averaged those so that they didn't misrepresent, if you will, the sea level acceleration in the world's ocean. And the bottom line is that if you look at his 1992 analysis, he determined minus 0.011, again, basically what we found. And when we redid this study, adding 25 years to his data, we determined about the same thing. It was minus 0.012. So even those are small, but they're consistent. I'll say a little bit about the satellite altimetry data. Again, the satellite altimeters went up in late 1992. And initially, there was a lot of concern that they were showing a rapid acceleration of sea level. And look at that a little bit in a minute. But again, we saw that sea level is noisy, and so we have to be careful what we accept. It takes a long record. I think we saw in one of the data group 1, it took 60 years of data before the data started to settle down. Well, here are the changes in trend from the satellite. And these, again, it went up in 1992. So here we have a 3-year average, and these are in millimeters per year. And this represents a 5-year average. You can see that they're actually decreasing with time. Satellites also have the difficulty that they tend to drift. And by the way, they are calibrated against tide gauge data, so they're not really independent. If you look at the panel that just came up and you consider the data from 2005 to 2010, the rate of change has slipped to 1.5 millimeters per year. That's about worldwide average over the 20th century. And also, if you analyze these data, the full record now, from November 1992 to April 2010, they show a negative acceleration. This plot shows the trend, the rate of sea level change from Holgate. And I won't explain this too well, but actually sea level oscillates. He feels that these represent the world's oceans. Sea level rate of change oscillates. And we saw this might be due to El Niños or other factors that we don't know. There are long waves, very long waves in the ocean that propagate around these oceanic basins. For reference here, we've shown the 1.7 millimeters per year. And then we've added the altimeter data. And you can see that the altimeter data are just, they're not exceptional. Changes as large as them have happened before. So I'll conclude now. We've analyzed long-term U.S. gauges, and we find a small negative acceleration during the 20th century. It's small, but it's a clear, I feel it's a clear signal. And also the worldwide gauges are basically completely in agreement with the U.S. gauges. Now this is surprising because most of the human effects, emissions of carbon dioxide, other effects, have occurred in the 20th century. So there's either a very long time lag or there's something we don't understand. I tend to think it's the latter. I think there are things happening in the world's ocean that dictate the sea level change that we do not understand very well. And basically, our conclusion is that these other effects dominate over greenhouse emissions. Now, what they are, I don't know. There is a lot of interest. There are a lot of experiments going on. There are satellites that now measure the gravity distribution around the world, and they're being used to determine whether some of the, for example, the Greenland ice sheet or the Antarctic ice sheet are growing or contracting in volume. So I think we'll know a little bit more later. I think clearly we need a longer satellite record for that to meaningfully contribute to our understanding of sea level acceleration. Again, I mentioned earlier that the 2013 IPCC findings will be out shortly. There's a lot of pressure to increase the 2100 range, and we have found that people don't like good news. I'd consider our findings and those of Bruce Douglas and many others, not many others, but a few others, that there is a negative acceleration. I consider that good news, but a lot of people don't seem to feel that way. And finally, I mentioned that the deceleration of 0.01 millimeters per year squared is small, but if it continues over the 21st century, it will decrease the present sea level trend from 17 centimeters per century down to 12. And so that, I think, is significant. It's a 29% decrease, even though it seems like a small deceleration. So thank you very much for your attention, and I look forward to the rest of the conference.